An electrocardiogram, or ECG, or the Dutch or German version of the word EKG, is a tool used to visualize the electricity that flows through the heart. An ECG tracing specifically shows how the depolarization wave moves during each heartbeat, which is a wave of positive charge. And the way it looks depends on the set of electrodes you're using. This particular set of electrodes is called lead 2, for example, with one electrode on the right arm and the other on the left leg. So essentially, when the wave's moving toward the left leg electrode, you get a positive deflection, like this big positive deflection corresponding to the wave moving down into the left and right ventricles. To understand the basics, let's start with an example of how we can look at the heart with only one pair of electrodes. A positive one and a negative one. Remember that at rest, cells are negatively charged relative to the slightly positive outside environment. And when they depolarize, the cells become positively charged, leaving a slightly negative charge in the outside environment. So let's say that when this set of cells is at rest, they're red. And then they turn green as the wave of depolarization moves through them. Now, if we freeze this wave of depolarization as it's moving through the cells, half of the cells are positive or depolarized, and half are negative or resting. And so there's a difference of charge across this set of cells. You can think of the charge difference as being a dipole, because there are two electric poles. And we can draw this dipole out as an arrow or vector pointing towards the positive charge. And remember, the electrodes detect charge on the outside of the cell. So this points toward where the positive charge is outside the cell. Now, if there's a dipole vector pointing toward the positive electrode, then the ECG tracing shows it as a positive deflection. The bigger the dipole, the bigger the deflection. If we unpause this, then everything becomes depolarized. And since there's no difference in charge now, there's no dipole, and so there's no deflection. Moments later, a wave of repolarization goes through. Pausing halfway through again, now the vector dipole goes in the opposite direction and faces the negative electrode, which means there'll be a negative deflection on the ECG tracing. Again, the bigger the dipole, the bigger the negative deflection. Now, even though it'd be nice if the depolarization wave lined up perfectly with the electrodes, usually that's not the case. So what we end up looking at is the vector component that's parallel to the electrode. For example, let's say the depolarization happened this way, at an angle. Then we'd break the vector into two parts, one going parallel with the electrodes and one going perpendicular. The one we care about is the one that's going toward the positive electrode, which causes the deflection. Though since this arrow is shorter, it's going to cause a slightly smaller deflection than previously. In other words, the size of the deflection on the ECG tracing always corresponds to the magnitude or size of the dipole in the direction of the electrode. The perpendicular component isn't pointing at the electrode, so it doesn't cause any deflection. In fact, if there's a depolarization wave that goes straight up, which is perpendicular to the positive and negative electrodes, then there'd be no deflection at all. In a standard ECG, there are 10 electrodes. 4 limb electrodes, one on the left arm, left leg, and right leg, and 6 precordial electrodes, V1 through V6, that wrap around the chest. And the right leg electrode is usually used as a neutral lead. Now, the heart's a 3-dimensional organ, right? So V1 through V6 line up in the transverse or horizontal plane of the heart. And each electrode is set up to detect any wave of positive charge coming toward them, which based on what we know already means that they're positive. These are collectively called the chest leads. Meanwhile, in the coronal plane, the non-neutral leads are called augmented vector right, or AVR, on the right arm, and augmented vector left, or AVL, on the left arm, both of which are represented as vectors that are 30 degrees up from the horizontal line. Finally, there's the augmented vector foot, or AVF, on the left foot, which anatomically isn't straight down, but it's close enough that it ends up representing the vector facing straight down on the diagram. Just like the precordial electrodes, AVR, AVL, and AVF each detect any positive deflection coming toward them. Now, in addition to these 3 limb leads, there are also bipolar limb leads called lead 1, 2, and 3. which are recorded using 2 electrodes instead of just 1. Lead 1 uses the right arm as the negative pole and the left arm as the positive pole, forming a vector that goes to the right. Lead 2 uses the right arm as the negative pole and the left leg as the positive pole, forming a vector that goes to the plus 60 degree mark. And lead 3 uses the left arm as the negative pole and the left leg as the positive pole, forming a vector that goes to the plus 120 degree mark. So in total, you've got 6 leads from the limb leads and 6 from the chest leads, leading to a grand total of 12, which gives you your 12 lead ECG. Now, the point of having all these leads is to get different views of the heart, making it easier to see exactly how that wave of depolarization moves through the heart. As an example, consider how the 6 chest leads, V1 through V6, register the depolarization waveform called the QRS complex. The exact same depolarization wave might appear mostly negative in V1 and V2. It might be isoelectric in V3, and mostly positive in V4, V5, and V6, all because of the exact direction and magnitude of the vectors at different points in time. Similarly, each of the limb leads produces its own viewpoint of the depolarization wave as well. Now, all the limb leads and chest leads can be grouped based on the regions of the heart that they're nearest. Problems in specific leads or groups of leads suggest that there might be a specific region of the heart that might be affected by a disease. Leads 2, 3, and AVF are inferior leads because they're near the inferior wall of the heart, which receives blood from the right coronary artery. Leads 1 and AVL, along with 2 of the chest leads, V5 and V6, are all considered lateral leads, because they're near the lateral wall of the heart, which receives blood from the left circumflex artery. Finally, V1 and V2 are considered septal leads, because they're nearest to the interventricular septum, and V3 and V4 are anterior leads, because they're nearest the anterior wall of the heart. Both of the septal and anterior regions are served by the left anterior descending artery. Alright, as a quick recap. In a standard ECG, there are 10 electrodes, 4 limb electrodes and 6 precordial electrodes that wrap around the chest. These electrodes are used to make 12 leads, each of which illustrates the movement of positive charge on the outside of heart cells. The ECG tracing shows a depolarization wave moving towards an electrode as a positive deflection, and one moving away as a negative deflection, each of which is proportional to the size of the dipole. The point of being able to get different views of the heart is that it makes it easier to see how the wave of depolarization moves, which provides valuable information about the heart's structure and function.